Alright guys, so today we're going to do a problem called 797, all paths from source to target. This is LeetCode problem of the day for December 30th, 2022. So the problem states, given a directed acyclic graph DAG of n nodes labeled from 0 to n-1, find all possible paths from node 0 to node n-1 and return them in any given order. The graph is given as follows. Graph of I is a list of all nodes you can visit from node I, and there's a directed edge from node I to node graph ij. Okay, so given this graph, we go from 1 to 2. Okay, so from the 0th node, you can visit 1 and 2. From the first node, you can visit 3. And from the second node, you can visit 3. And from the third node, you can't go to any other. So the paths we can take is 0, 1, 3 and 0, 2, 3, which you can see in this output here. So the output is a list of lists where you're outputting the path and how each distinct path. So here we go from 0 to 4, and we're asked how many different paths there are. So there's 0 to 4, 0 to 1, 1 to 2, 2 to 3, and 3 to 4. So 0 to 4, 0, 3, 4, 0, 1, 3, 4, 0, 1, 2, 3, 4, 0, 1, and directly to 4. So all possible paths. So let's take a look at our restrictions. So n must be between 2 and 15. Graph ij must be from 0 to less than n. Graph ij being a node, quote unquote, member. Graph ij is not equal to I. There will be no self loops. All the elements of graph of I are unique. So all these elements are unique. And the input graph is guaranteed to be a directed acyclic graph. So the idea that it's acyclic, meaning that it's not it doesn't go in a cycle, it's very important because that means we can assume we can DFS through the whole thing without ending up in a situation where you're in a loop. So I think the idea of this is pretty straightforward. We get this into a situation where edges are easily traversable from a given node, and then we visit from each node, 0 to 1, 1 to 3, 2 to 3, so on. And of course we have memoization, so we've already started at a node. We can know what the output will be. Okay. So goal, return all possible paths in the form list of lists from 0 to n-1. Inputs, we only have one parameter, which is the edge connections for for edge connections for a given node. Output, return the list of lists showing possible paths. And the way we'll do this is through a DFS. DFS through the graph. So convert graph into dictionary or unordered map format. DFS through the graph starting from 0. If the DFS reaches n-1, record that as a result. Memoize the solutions. And we can use backtracking so that we so that we record all possible roots from a given node. Okay. So, for example, if I DFS from 0 or here, if I go 0 to 3, I know 3 goes to 4 directly, so I can memorize that. If I go 0, 1 to 3, I know 3 goes directly to 4, so I can just grab 3 to 4. I've memorized that already. 0, 1, 2, 3, and then I can memorize that and so on. And 0 to 1, well, I have multiple solutions for 0 to 1, so I would memorize that. Okay? So let's go ahead and write the DFS function, and we start at a given I. We have n is equal to length of graph. We have our, what do we call it, edges is equal to a dictionary. Default list. So for node collection graph edges at I. Edges at I dot extend node collection. Well, hold on. We don't need to put this in a default dictionary. I'll take that back. So we go into this DFS and we say, okay, at this ith position, for next node in graph at I, we'll say we'll DFS next. So starting at, let's say I start at let's say my next node is going to be 4. Okay, so from 4 to the end, I'll get a array. So we'll call this paths. So, and we will have this, our result. Say paths, okay. So for p and paths, p dot insert at 0 position I, res dot append p plus, so concatenate this. I plus P. So what I'm saying is that, okay, I go from 0 to 1 and I DFS that one. 1 will return 1, 3, 4 and 1, 2, 3, 4. And so then I need to append that to the result here. Okay. And then we'll have our u cache back size equal to none. And then, of course, we'll have the base case I is equal to n minus 1. Return I. So return DFS at 0. Okay, so what is happening here? So the idea is I go to 0. I start at 0. I say DFS 0. Is 0 equal to n minus 1, which would be 4 in this case? No. We continue. We have a result. For each next in the graph, so that's 1, 3, and 4, I go 1, and I DFS into 1. Now for 1, I go into 2. 2, I go into 3. 3, I go into 4. 4 is n minus 1, so I return this array with the 4 in it. Now I'm here. Now I pin the 4, 3, then 4 into my results, and then I pass that to here. Then I pass on 2 to 3 to 4 here, and then I go from 1. So that's 1, 2, 3, 4 for one of the results. Now I need to go 1 to 3. That's already been memoized by LRU cache. So 1, 3, then 4. And then I'm going to go 1 to 4. So that's pretty straightforward. And then 0 to 1, 0 to 3, 0 to 4. And that's what I return. So we run this. That should be the result. Okay. So that is how it is. Now the question is this as efficient as I can get it? The time complexity for this is going to be O of n, I believe, because we've memoized the solutions. So we only go visit each node once. Every time we revisit a node, it's only going to be O of 1. So it's trivial, since we've already memoized it. So it's going to be O of n time complexity. And for the cache size, it's going to be O of n as well, since we're saving for each node a certain number of paths. So we're going to go ahead and submit this and see how it does. And see if it passes the time complexity. And it does. It beats at 76% with a bit of memory usage. Now, before I go to the solution I want to talk about, there is probably a way. Actually, no, this is a backtracking problem, so there's no way to do this with tabulation. So this is a iterative DFS with, and backtracking, of course. So we're going to take a look at Lee. Count from start to top in topological order, count by DFS with memo. Both of them have time O of edges and O of n space. Let me know if you agree here. O of edges, O of n space. Yeah, I think I can agree there. So he didn't do memo here, but essentially, okay, so he passes in the path as well. Okay, the time complexity is 2 to the n. So we have n nodes, label O to n minus 1, j by less than j, edge. Three. So that is 2 to the n. Okay, so that is the solution, and I've managed to do something that somehow is more cleaner than the others. Interesting. Okay. Well, all right. That is it for today's medium problem. I hope you were able to learn something. Thank you for watching. Please leave a comment down below. Let me know what I can improve, and I'll catch you next time.